Okay, I want to have a small discussion on integrals and really what they are. And I think most of you at this point have probably looked at the integral as the area under the curve. Again, you've taken the integral of a function and realized that it involves the area beneath the curve. Typically, the curve, at least early on in your career, is always bounded by the x-axis or the t-axis in this case. And you know that you're going to break this up into rectangles, and you're going to find the area of each rectangle, and you're going to add up all the rectangles to find in the total area. But I think I would encourage you really to think about integrals as the accumulation of something over time or over space. And I want to look at these examples and really talk about what they mean in this particular case and why they really make sense. Again, integrals accumulate, or they're a summing function. So in this case, let's look at v versus t, and we have this ever-changing velocity. So v of t is the velocity, and it would be like in meters per second. And what we would do if we wanted to integrate it, well, what are you doing? Well, you're accumulating each one of these little spaces, okay? So if you think about each one of these rectangles, well, what are they? Well, each one of these rectangles, if you make the rectangle small enough, then they have their individual speed at that moment, or velocity really, at that moment, and it's over this interval dt. And so what happens? Well, you integrate the velocity function for each moment in time from some t1 to some t2, right? Start somewhere and go somewhere. Lots of times we'd integrate from 0 to, let's say, like this was 0 and this was 5 seconds. We'd integrate from 0 to 5 of the velocity, which is a function of time, right? It's changing over dt. Again, dt is the infinitely really small width here. So you take each velocity times each time, well, that gives you the distance you travel each one of these rectangles, and then you add up all the rectangles. Again, what does the integral do? It accumulates all those rates at different times and sums them up. And again, you can't go old school and just take distance equals rate times time, even though that's all an integral, at least in this particular integral, is doing. It's going old school. Normally, back in, I don't know, 5th grade, you did distance rate times time because the rate never changed. Well, what if the rate is some function of time? Well, then you have to break it up into really small time intervals that we call dt. You still are doing a rate times a time to get the distance traveled over that particularly small interval, and then you sum them up. So in this case, this would give you the displacement. And if you're not changing direction, then again, displacement and distance traveled would be the same thing. Again, we'll look at a future example where they are different. In this case, they would be the same number. Let's say, you went so many meters to the right. Again, you're accumulating a rate over time and then getting some accumulation. In this case, accumulating velocity over time gives you displacement. Okay, what about down here? You had some R of t, which is like, let's say, your calorie burn rate. So you go into the gym, you get loose, then you really hit it hard with some higher intensity, and then you do some cool down. The area under the curve here, right, this area would represent the total calories burned. So total calorie burnt. Okay, and how would you figure that out? Well, again, you're going to accumulate. Let's say we started at 0 this time. Let's say we went to 10 seconds, or actually 10 minutes. This is a 10-minute little spurt here of exercise. Integrate from 0 to 10 of our calorie burn rate, R of t, and then dt. R is some function of time. Each individual rate has its own little bitty t. Again, theoretically, we're breaking this up into really small intervals. And we accumulate all of those rates times their times. We accumulate all these individual calories, and we add up all the calories burned from each section, and then we get the total number of calories. So this answer would just be calories. It'd be the total calories burned in that particular time interval. Okay, how about this one? What if we integrated the flow rate? The flow rate might be the number of gallons per minute that's, you're dumping into a pool, or that's the number of gallons per minute that's leaking from something. Again, the area under the curve would represent the total number of gallons going into the pool. And again, we would break this up, as we always do, into rectangles. But really, we would integrate, let's say, I don't know, this is t equals 8. So maybe integrate from 0 to 8 seconds of the flow rate dt. And again, it's the accumulation of a rate over time to give you then that total number of gallons, right? The answer here is so many gallons that either, in this case, if it's a positive flow rate, when we might talk about we're filling something. Okay, another physics example, we could look at the acceleration. Again, acceleration is in meters per second per second. I know we talk about an acceleration being meters per second squared, but this will make more sense, I think, because we're accumulating acceleration over time, which is going to give us a change in velocity. The area under the curve here is how much we've increased, in this case a positive acceleration, we've increased our velocity by, right? Integrating acceleration from, let's say, 0 to, I don't know, 5 seconds there of an acceleration curve. Again, we break this up into little rectangles, and what does each rectangle represent? Well, each rectangle has its own little bitty acceleration rate, right? At that moment in time, you have a particular acceleration for a certain amount of time, but if you accelerate for a certain amount of time, this represents a really, really small change in a velocity. And you add up, you accumulate all those little bitty changes in velocity, and then you get the total change in velocity in that time interval. And if you knew the starting velocity, well, then you could just add or subtract the change in the velocity to find your new velocity at the end of that 5 seconds. Again, the area represents the accumulation of that particular rate. Accumulating acceleration gives you a change in velocity, just like accumulating a velocity gives you a total change in your position, which we would call displacement. Okay, now those are all positive ones, and now we can look at a little more complicated ones in which there might be some change. What if our velocity curve looked like this? You're like, well, there's area up here, and then there's area down here. Well, what's the difference? Well, one's just an accumulation of a positive rate, one's an accumulation of a negative rate. The area up here represents how much you move to the right, and down here you're just moving to the left. It looks like this area is bigger than this area. Let's say that this area was 10, okay, and that this area was, let's say, 25. Okay, so here's the difference between distance and displacement, and the difference sometimes between the integral and the area. If you just straight up did the integral from here to here, you're going to get a negative 15, right? The integral of velocity is going to give you a negative 15, because that's going to count. This is positive and this is negative, which is what the displacement is, negative 15, which is going to say you moved 15 units to the left in that time interval. The distance traveled, well, that would be the integral of the absolute value of velocity. And that's actually the total area, not counting whether it's positive or negative. And that's going to give you 35 because you walked 35 total meters. You walked 10 meters to the right and then 25 meters to the left. Again, the difference between distance, which is a scalar, and displacement, which is a vector, also come up in integrals. Again, the integral and the area aren't always exactly the same. The area would represent the distance, where the displacement, well, you'd use the areas, but that's a negative displacement. Well, because you're moving to the left, this is a negative velocity here, a negative rate. Same thing here. Here we'd have a negative flow rate over time, and then a positive flow rate over time. Hopefully, we can see that this area is much bigger than this area. So let's say that area is 5, and this area is 20. Then what could we say about the total number of gallons? We could say that the total number of gallons is a positive 15. Meaning, I don't know how many gallons we started with in this big old barrel we're filling up, but I know that at the beginning, 5 gallons leaked out, and then we put in 20 more gallons, and so we had a plus 15 in terms of our net. Again, the area is 25. That's how much each one of them changed a little bit, but the total would be 15. Same thing here. We're talking about the rate. This R could be like the rate of people per minute that's coming into your classroom. Right at the beginning of the bell's going to ring. Before the bell rings, a couple of people come in, then more people are going to come in, and then the bell almost rings and everyone's in there. And then there's no change, and everyone would then leave. And again, maybe people would leave at first, then a group leaves, and then the stragglers leave. And again, these areas, well, they should be the same as long as everyone who came into your room and left your room. If you integrated from 0 to say 20, you actually should get 0. Right? There's no actual net accumulation. This one is kind of special because it's the only example I've given in which it's x instead of time. Almost all these application problems involve time except for this one, and this is a great physics one. If you accumulate force over a distance, again, this force is a variable force, that this distance and displacement, these are all different, and well, then the force stays the same for a little bit, and then the force actually gets weaker. And you want to find this area. In this case, the area represents the work. The work done, meaning, and again, the classic example is stretching a spring. You'll get to this at some point, no big deal right now, I'm just giving you this as an example. Springs are usually linearly proportional to their displacement. So we would say Hooke's law says that F equals negative kx. Don't worry about the negative sign right now, it just tells you a direction. But it says that if you stretch a rubber band or a spring, it gets more and more and more difficult to stretch it. Now that's not what this graph is. This graph of F, well, that's nice and easy, just a linear function. But it says that the force grows with displacement. It's a function of the displacement. And so you have to actually integrate over that entire displacement. Here your bounds are some x1 to x2. Lots of times it's just, okay, how much work does it take to stretch it from, 0 to, 0.05 in terms of centimeters or something. Okay, but again, accumulating force over distance is the work done. So hopefully all these examples have given you a pretty good idea of what an integral does. Again, I think a lot of people start out talking about the integral as the area underneath the curve, but the area represents something. It's the accumulation, it's the summation, it's adding up all the individual rates over time or over space and then giving you some total change. Okay, you do have to be careful sometimes when they're talking about a velocity versus time graph where they're looking at the distance, which is the sum of the areas, or they're asking for the displacement.